We now look to the notion of named streams in OS. We call it ports. So this is the only extension we are adding to our declarative model. We have threads, of course. That's what I mean, the concurrent declarative model. So here is the way we see it. So a port is a named stream. It means it is an association of a name and a variable that is going to be bound. This will be bound as a list or an incremental stream. So it's a name that's stored then the stream S under a unique address, and this is an OS name. And the stored stream will change over time. How that will change? It will change by sending messages to that port. Okay, so S will be always the tail of a message stream, and sending a message M will add to the end of the stream, as we will see. So here we have our port, the association between a stream variable and a name, sending a message to the name. We look to the association, the stream that is associated with that name A, so it will read the stored stream S from the address A. It will create a new store variable S prime, and it will bind S to the const cell M followed by S prime, and then it will update the association. So A now will be associated with S prime. So the state of the port changes over time. Initially, the name is associated with the stream S before sending the message. After sending the message, the name is associated with the stream S prime. So what are the language primitives that we have? We have two language primitives. To create a port, this is the operation. So new port will create a port and associate a stream XS with that port. The port here is P. Sending a message will be a procedure, send, that takes a port and sends a message X. So let us look to an example. Here we declare stream S and a port P. Here we create a port. So at this point P is bound to a port, which is association of a name to a stream. Here we can browse that stream. So initially the browser will display just an unbound variable. In fact, it will display a read-only view of that unbound variable. Now if we execute send on this port the message A, that's an atom, then S will be changed to a list with the head A and another unbound variable. This unbound variable will be associated then with the port, with the name that is provided by the port. If we send a B, you will see that the stream S will be incremented step by step. Now the question comes as follows. Assume we declare a port here, and we look to that port, as you can see in this point, and then we create two threads. The first thread will send on the port the message A, and the second thread will send on the port the message B. So the question is, what will the browser show? Here is an example of, in fact, non-determinism. These two threads will be executed by a scheduler. Scheduler is in the engine of the system, and it will schedule these two threads for execution. It might schedule this thread before that thread, which would mean that A will be sent before B, or it might schedule this thread before that thread, which means that B will arrive on the stream before A. And that's what we can see. So what the browser will show, it will show either A followed by B followed by the rest of the stream, or B followed by A followed by the rest of the stream. So for the first time now, we see we have non-determinism in the system depending on the scheduling times of the different threads. For the first time, we see that we moved from the functional declarative concurrence model, where the results are always function on the input, to a non-deterministic execution where we might get different results. So now let us go further and look what we can do with messages. We can include a port P prime as part of the message. So the sender can send a message, and also a port that the receiver will answer on this port. So the receiver sends an answer on P prime. That is the port. So basically it will do a send on P prime and answer message. And this is what we see in message passing system. We send messages to each other. We include addresses of the senders in this message so that the receiver can send back a result or a response. Here is another way which we can do using the single assignment data flow variables, is that we do not send an address in our message, but we include in our message a pre-addressed reply envelope. What is that? That is actually just a data flow variable. This data flow variable is accessible to the sender, the source of the message. And once the receiver gets this data flow variable, the receiver can bind this to an answer. So just take the data flow variable, bind it to an answer, and this answer will be visible at the sender side.